This good, maybe good morning your side, or good afternoon, good evening. Welcome to our chapter 5. In chapter 5, we are going to look at a number of topics. So we are going to look at soil water, permeability, and flow. So in soil water, basically we shall briefly talk about capillarity. In permeability, basically we shall look at how water flows through a soil material. So there's the measure of how water flows, what we shall call permeability. Then flow, we shall look at how water flows and the dam and the sheet pile through a concept of flow nets. So soil, all soils are permeable materials, water being free to flow through the interconnected pores. So for water to flow through a material, there have to be voids, which we shall call pores, which are interconnected. The reason why clay is we say it is impermeable materials, because for the clay is so fine, and the particles are held together by suction force, or what we call cohesion, that there are no presence of it. Although it is highly porous, but the pores are not interconnected. That clay is out of pores, but those pores are so minute and they are filled up, or the particles are held so close together that those pores, they are not interconnected. And between solid particles, the pressure of water is measured relative to atmospheric pressure, and the level at which the pressure is atmospheric or zero is what we shall call ground, the water table, or the rhytic surface. So below the water table, the soil is assumed to be fully saturated. That is true. So that the pore water can easily flow through a material which has fully, remember, water will flow through as a fluid flows through a pipe. Now for the water to be flowing through those interconnected pores, it is likely that due to the presence of small volumes of trapped air, the degree of saturation will slightly be below 100%, and obviously this will affect the permeability of such a material, or how the seepage, how water seeps through such a material. So we will assume that the condition of seepage, the material is completely saturated and lies below a water table, okay, or at a level above which or at which the atmospheric pressure is equal to 0. So the level of water table changes according to the climatic conditions, but the level can change also as a consequence of construction operation. Why? So when you are constructing a structure, let us take this structure. If for instance, if this is static, at least the water in the ground and the water is not moving, is that okay? When you put up a structure, that structure will transfer what we call an increase in effective stress at some point. And so that stress or pressure will be exerted onto the water, and that water will cause flow. Is that okay? So therefore, we say that the water table can change. Now, when the flow occurs, obviously the water table changes. Okay, because the water will be flowing, it will tend to reduce. As we shall see in what we call in well analysis. In well analysis, we shall say that when you pump out water, the water table depresses. So as long as the water is withdrawn from the well, whereas the water table reduces. So there can be a change. Is that okay? It can be due to the construction, which bring about flow of water through that material. But also we have to be careful. For instance, there are people who look for what we call groundwater sources to supply water for use through digging of boreholes. So when you are digging a borehole, you may counter two structures. You can counter a confined aquifer and also what we call a patched aquifer. Is that okay? So a patched aquifer, it occurs when within a porous material there is a deposit of sand or it's a deposit of clay. Okay, the deposit of clay within a small area will cause to be able to hold water. Is that okay? And but you may find that the real aquifer is below that deposit. Is that okay? So when you dig your well, you may locate water within the parched aquifer. And during the dry season, you have seen that such wells do dry up. Is that okay? Because you have no source of water. Normally, these aquifers are fed either there is a mountain with a glacier this side, water flows under it, or there is a lake somewhere or a river which feeds these aquifers. Is that okay? But for punched aquifers, normally they are fed with only rainfall. And so if there is no rainfall, what happens that material the water dries out. So it's very important. So therefore, it's very important to do what we call a pump test. When you are, for instance, you are looking for water for supply through boreholing, you have to, or through groundwater supply, you need what we call a pump test. A pump test, you do it for 3 days, pumping water to see that if there is a yield of the well, so to see that if the water comes back with the well. If water doesn't come back that way, it means that one may have been a punched aquifer. Okay. So also there's a condition which occur which called the artesian conditions. They occur under condition of what we call confined. This is unconfined, but when you confine water between a rock and a layer of clay, we say that clay, although it is highly porous, but it is impermeable because it lacks interconnected voids or pores. Voids through which water can flow. For such clays, they form what called, if there is a deposit. Now, for water can be confined in between that. You may find that where the water comes from, it will tend to push the water. If there was no this aquifer, water would have flown to this other level, which called the piezo or the piezometric surface. This water would flow to this level if there was no this aquifer. Is that okay? So in that what we're bringing about that when you dig a well in such an aquifer, if the piezometric surface is above the groundwater level, it brings about a well or a spring, water be able to flow out. Is that okay? Because this is the line, what we call the hydraulic line or the potential difference line. Okay, the potential difference line, what we call the piezometric surface. So along this surface, water would rise to this surface. Water would rise to this surface without the confinement of this upper layer. If this layer wasn't here, is that okay? Would rise to this. What we call now, this would be the hydraulic line. What we call the flow line. The hydraulic line, giving us an hydraulic gradient, which allows water to flow. So with this, what we call now, for a portion of a confined aquifer in which the piezometric surface is not only above the ceiling of an aquifer, but also above the surface. Now, this is just what we call an artesian aquifer. A well in an artesian aquifer is a flowing well. It allows water to flow out of that well because water tends to come to this to this level. There is pressure. There is that pressure to come to that point. So we have seen so to dry flow, this is an equal sign. To dry flow through an aquifer, so we can go back to what called Bernoulli's principle, which is the hydrostatic head to be H. If you have 2 points and you have a point of reference somewhere, now this is your H. So H should be the flow, will be equal to velocity over 2g plus P, which is pressure, divided by this term, which is the unit weight of water, plus M. This will do this for in seepage problem, atmospheric pressure is taken to be 0, which will be this one here. For this part here, and atmospheric pressure is taken to be 0, and the velocity is so small that the velocity head becomes negligible. So the velocity head, this one becomes 0, Is that okay? And therefore, the electrostatic head is therefore taken as to be. Now, if the pressure is so different, now for this one derived from that. If you remember in fluid mechanics, your Bernoulli's principle, so we would get that our head is equal to P over unit. This is pressure, and pressure plus. So we shall fully look at this. We shall fully look at this when we go to what we call the seepage analysis. What we call the effective stress versus the effect of having the effective stress having a higher hydraulic gradient. So the hydraulic gradient, which is equal to P times H plus N. So we're saying introduction. We are saying that above the water table, the water can be held at negative pressure by capillary tension. So when water, for instance, if this is the water table, but due to the sizes, if this is a fine-grained soil, remember for capillarity, if you remember our experiment which we used to do in our lower classes, if you have a small tube and a bigger tube, and you allow in mercury, and you open to the same atmospheric pressure, so we find that mercury would rise due to the adhesion forces between the walls of the tube and between the part and the molecules of mercury. Mercury would rise higher when the tube is smaller compared to both open to the atmospheric pressure. So this phenomenon is what we call capillarity. So let's remember, we see that clay has very fine voids. So water can easily rise through a clay material due to capillarity. So I find that near above the water table, I find that this area may be highly saturated. And when you have a saturation, remember this pressure will be at negative pressure. Will be at negative, so it will be unit weight times H, where H is to the depth of saturation by capillarity. Is that okay? And then if now we were to find the effective stress at this point, remember effective stress is equal to total stress minus, but this is a negative. Remember that now for somehow capillarity somehow increases the effective stress. Okay, because if you put a negative here, they become total stress plus unit weight of water times the depth at which the layer which is saturated by capillarity. But below the groundwater table, obviously, this is old, it will be a negative. Is that okay? This one will be a negative. Is that okay? Why? Because here the pressure here, the power pressure is a positive and not negative. Remember, it is at below positive but above negative. Why? Because of the negative pressure of water held above the water table results in an attractive force between particles. And for the particles are held together, this attractive force, hence improving the effective what? The effective stress. So if I can say that, we say that above the water table, the water can be held at a negative pressure by capillary tension. The smaller the size of the pores, the higher the water can rise above the water table, as I said, using this. If we use this illustration here of mercury in this big and small tube. Now for the soil can be almost completely saturated in the lower part of the capillary zone, this part here, part of the capillary zone. But in general, the degree of saturation decreases with height. Obviously, when you go up with height, over the degree of saturation will decrease. When the water percolates through the soil from the surface downward, when it comes from this side here, the water table of this water can be held by surface tensions around the points of contact between particles. Now, for this surface tension brings about what we call the cohesion. That's why you can, when you wet clay, it becomes highly cohesive because of the surface tension of between those small parts and between the points of contact of particles brings about that attractive force. And this negative pressure of water held above the water table results in an attractive force between particles. This attraction is referred to as source function and also is a function of power. You understand? So this particle, that's why I said when a material is so fine, is highly, although it has a lot of voids, or it's highly porous, sorry, it is porous, but it is highly impermeable. Why? Because of this. Now, for the smaller the particle, the smaller the pore sizes, the smaller the pore sizes, the higher the attraction of these particles together. That's why when you wet clay, the particles are attracted together. You can mold it. Is that okay? You can mold the clay. It becomes very cohesive because of this suction force, the pulling force. The suction force is the pulling force of particle between two particles. So we have talked about now the soil water. Now we look at the permeability. So in permeability occurs in one direction. If you to take in one direction, water flow through a saturated measure. The material has to be saturated, following Darcy's law. So what does that is? Darcy's law said the velocity through the water is directly proportional to the hydraulic gradient. Is that okay? So what is an hydraulic gradient? If you have to, if this is your source of water flowing to this other side, and if this is H and this is L, the length, is that okay? Now for our I, the hydraulic gradient, which allows water to, because the stiffer or the bigger the hydraulic gradient, the higher the velocity. Is that okay? Given by H divided by L. Is that okay? So enough, we can say V, the velocity through velocity is like a proportion through a material or through a soil is like a proportion to H over L. Now to remove this, then we can put this proportionality constant. We can say that V is equal to K H over L. Is that okay? But what is Q? Remember that flow, what is the amount of volume of water which flows per unit second, is equal to volume times area from our fluid mechanics. Is that okay? So if you have the V, then we can say enough is equal to K. We substitute for V. Now for Q is equal to K A, the area in which, perpendicular in which the water is flowing, into H divided by L. This is the constitutional area, which is perpendicular to the direction of flow. This is area. So now for if you have this is equal to Q is equal to Q. Now which is equal to L over B. Now for instance here, so to get now, if you divide by A throughout, obviously, you may find that V, obviously, Q over A, if you put Q over A here, now for this one will cancel out, which will remain with our V, and this one will cancel out, which will be K, H over L, which H over L is our I, we call the hydraulic gradient. Is that okay? Now you can make K here the subject and determine your what? If you have the amount of water which you collect per second, volume, then you have the length of a sample, of your soil sample, the length of a soil sample. Is that okay? Then you can, and you have the H, between the gradient and the elevation of the tank. Then you can determine how much water flow through, and we shall see how we done it in the lab, how it is done in the lab. Where Q is a volume of water flowing per unit time. A is the cross-sectional area of a soil corresponding to flow Q. K is the coefficient of permeability which you want. To measure the ability, which measures the ability of water to flow through a material. The coefficient of permeability primarily depends on the size of pores. It depends on the size of pores, but also particles, and also depends on particle size. Talking about clay, the impurities, it depends on void ratio. The degree of saturation also depends on entrapped air. Is that okay? And also sometimes it depends on the crack. Sometimes the material may be cracked, or it has roots of trees. Sometimes it has the impurities, that are what you call the impurities. Sometimes it has termite tunnels, or what you call the antil. So such sometimes affects the permeability, the K value, or it reduces the K value. So for instance, if you have a soil which is highly infected by termites, those termites they make tunnels. So if water flows through that material, it may be faster. Remember, K is measured from this expression. You can see that area. We can we see that if you make K the subject here, you can see that is equal to Q over A into I, which will be L over H. Is that okay? And this is Q. So if you divide Q is meters per cubed, meters cubed per second. So you divide by area, it becomes meters per second. So you can see that our K is in meters per sequence, which is meters per second. Is that okay? So now for this meters per second is speed, is flow. Okay, and the presence of a small percentage of fines in coarse grained soil result in a K value significantly lower than the value for the same material without fines. Now, if I say that now for the presence of fine materials, or the particle size also affects the value of K. If you have a material which contains very fine particles, for the value of K will be lower. For a given soil, the coefficient of permeability is a function of the void ratio. And the function said so. If a soil deposit is stratified, the permeability for flow prior to the direction of stratification is higher than for flow perpendicular direction of stratification. We shall see that. So the presence of fissures or cracks in a clay results in a much higher value of permeability compared with that of unfissured material or uncracked material. So if you have cracks in clay, obviously enough for the ability for water to flow through it will be high compared when it is not fractured. Is that okay? Or it has no fissures or cracked. Is that okay? So next time we are going to look at how to determine K permeability. How to determine K. Okay. So we are going to briefly, in our next discussion, we are going to see how we determine K. Exactly. So before we go, we can look at the first part of it. The values of K for different types of soil are typically within the range shown in the table below. For sand, and this is a guy, show that the proximity value of K is given by remember this is the effective size. Is that okay? Remember, without plotting or time the effective size, it is at this percentage passing, you come to where 10% is. 10% is, you plot, then you come down here. So this will be in millimeters. Is that okay? That will be the effective size, D10. Normally, D10 you can determine for coarse grained soils, not for fine grained soils. For coarse grained soils, you can be able to predict the ability of water to flow through it using this equation, and this comes in out in meters per second. So, but for the different ranges of or types of soils, you can find that for unfissured or uncracked clay, okay, which has clay content which is greater than 20%, maybe silt clay soils, but with a clay content greater than 20%. You see that the permeability, the speeds are normally, it's literally impermeable. Okay, while you can see that for clean gravel, it can range from 1 meter per second or to 0.1, which is this is somehow a bigger speed. Is that okay? So why are these K values are important? These K values are used in hydrology to determine the effective runoff. So you can use the K value because remember this is a measure of permeability or infiltration, measure of how water will influence. Now, if you can determine the amount of the head which can go into the ground, then you can determine the head which can run off. Is that okay? So also where it is applied, it applies in stability analysis of earth structures. So we shall look at that briefly as in our next class. Stability of structures, of earth structures, and earth retaining structures subject to seepage pressures. So that times you if this is the head, now for this will be the times W. This one will be times this one will give vertical under pressure, the water pressure, or the thrust. The thrust. that okay? The thrust. Now, if the thrust is greater than the effective stress, if the thrust is greater than the effective stress, what happens? That the material will start heaving, or it first piping. If water will start coming out, because the static pressure or the hydraulic pressure is much greater than what? Now, if you can, this one is good to design. How my friends, if it is you are designing you are feeding into a swamp, you need to determine how much water, how much fill should you do, so that you don't have water rising through the fill. To determine this X, the amount of fill to put back, or the fill material. So that is very important. We have to design that. It depends on the pressure at which water can rise. Okay, what we call the hydrostatic. So the thrust pressure is okay, the thrust or the pressure at which water can move through the material. So we shall see that. That's why it's important. Another thing is to solve problems involving piping seepage. Water from excavations. Okay, so when you excavate through a material and you find that the water table was near, is that okay? So when you start excavating, you find that water will decide to come out, because you remember this may be the confining material, maybe an impermeable clay. So when you reduce an impermeable clay, or the weight or the effective what? If you reduce the effective stress here, what happens? The thrust. This equation also the thrust or the hydro pressures or the water pressures will be greater than the effective stress. Therefore, the heaving will occur. Water will start pumping out or piping out. Is that okay? Through the excavation. So we are going to look at what we call the seepage pressure and the velocity at which a material water moves through pores. So it's very simple. So the seepage velocity, remember using, if you have a material, that remember assume this is soil. Okay. Let us assume this line here. This is a line of interconnected pores, or the voids, and the voids have the cross-section area. The cross-section area VA. Okay, and this is the soil, and this is the total volume of what? Of soil, which is A. Is that okay? So using the continuity equation from fluid mechanics, you know that V1 through the soil sample times A1. This, for continuity, this is equal to, if the vessel is interconnected and is under the same hydrostatic pressure, so is under the same pressure difference H. Okay, now for is equal to AV1 which is the area of the void times the seepage velocity through the void. Is that okay? Which is equal to Q, as you can see, which is equal to Q. Now, for instance, if you cancel this one, now for our V is equal to Q over A. Is that okay? Q over A. But you know that also velocity is equal to VV, the volume of it divided by total volume. Is that okay? But we are assuming that the length of the soil and the length of the interconnect of the void is the same. If you make our L the constant, if this L is constant, is that okay? We have now for this one here will translate into area of voids times L, since the same length, then divided by total area of the sample times L, because L is the same. Now for L cancels out. So now for our process comes to be AV over A. Is that okay? Now we can say our AV is equal to N times A, where A is the area of the cross-section area of the sample, of the soil sample. Is that okay? So we can substitute in this equation here. That this equation for our V is equal to Q over N times what? Times A. Is a fraction. Is that okay? Now for what happened that Q over A is discharge velocity. Is that okay? Or the velocity of water which pass through the sample, discharge velocity. Is that okay? Therefore, remember Q over A is velocity from this equation. Therefore, this is, if you make V in our V subject, and B to be Q over A. Now for Q over A, this part here will be equal to V over N. But what is V? We said this V, discharge velocity, is equal to K from dash 0, Ki. Is that okay? Now if we just put Ki over N. So now for the discharge velocity can be determined, the seepage velocity can be determined as V prime, which is equal to K, which is the permeability of the sample, times I is the hydraulic gradient between 2 points of interest, which hydraulic water, which is equal to H, which will be the H is the head, okay, divided by our L. L is the length of the sample, this is be the head or the pressure head. Is that okay? The pressure head, the pore water pressure head, which the one which causes flow. Is that okay? You can determine. So with this parameter, you can determine the velocity or the water at which the speed at which the water passes through the voids. Passes through the voids. So now we are going to look at the method of determining K. For that purpose, from this equation, we need K. Is that okay? So in this equation here, this is K. So K can be determined either using this, if it is the sand material, you can predict a K from our particle size distribution, or if it is a fine grained material, then we are going to see how we do that.